Yes, feel free.
Sure. Hello, my name is Pravat Vadim, and today I, with my respected colleague Anastasia Martinova, will tell you about artificial intelligence applications in parking lot occupancy detection problem. So let's begin our talk with a little motivating example. Have you ever had a problem with searching for a non-occupied parking lot? Probably in Western Europe it is not a big challenge, but in another parts of the world it can be quite a hard problem, especially in Eastern Europe and America and in Asia. The main reason behind such situation is lack of officially allocated parking spaces on the streets or in special areas and underdeveloped policies regarding the parking in the yards. In this slide, you can see the typical yard somewhere in the middle part of the Russia, for example. However, it is not the terminal stage of the parking issue. In some cities, like in some St. Petersburg, it is the second largest city of Russia with population that exceeds 5 million. We can observe such situation where cars occupy not only the side of the roads, but its center part too. Um, Unfortunately, despite the clear violation of multiple policies, such as practice emerged to be something normal for citizens of St. Petersburg as the population becomes larger of St. Petersburg and the city become overcrowded. Similar situation could be observed not only in this city, but in other cities of Russia, and not only Russia too. Okay, the last example will be too apocalyptic, I think so, because if you were so unfortunate to once park your car in such a location, in the next morning you will not find a way out just from this drop. Okay, but let's shift our focus from these a bit exaggerated examples to something more relevant to the actual statistics. The parking lot problem is influenced by two actual trends, motorization trend and urbanization trend. Despite the expected decrease of the number of cars per thousand of people in Europe, in other parts of the world, it will grow, certainly, especially in the locations where the uh, parking issue is expressed at most nowadays. Okay, what do we expect from the solution of this interesting problem? We need to establish such system that will solve three questions. That will solve three problems. First of all, we need to detect from some observation infrastructure non-occupied parking lots. Then we need to establish some route from the current user location to these observed free parking lots. And additionally, it will be extra beneficial to predict future availability of parking lots. Will they be empty after 10 minutes or 20, for example? In our current study, we will focus mostly on the prediction of the real-time availability. Well, and how our solution can be expressed in terms of application, for example. Okay, it can be a client-server app that is connected to some observation system based on video cameras. These video cameras can be connected together to broadcast the images, for example, once per 60 seconds. This broadcast is then translated to the predictive algorithm that will identify in defined desired locations. Are there other any empty spaces that can be occupied by your car, for example, or not? In such setting, we can formulate our task as a binary classification challenge. And if we are talking in this way, we can just shift further to the possible approaches that can solve this binary classification task. So, when we are talking about mm, image processing and machine learning, the one of the first things that come to our minds is convolutional neural networks. It is the really old architecture that was established more than 20 years ago by Jan de Koon. It consists mostly of three types of building blocks. First of all, it is convolutional layers parameterized by their kernel, obviously. The second one is large variety of different pooling operators and batch normalization, of course. Well, the key properties of convolutional neural networks are the following. First of all, it's their depth. Such architectures as VGG and ResNet have demonstrated that number of convolutional layers can significantly increase the generalization ability of neural network. However, there are interesting problem that is known as vanishing gradient problem. So it was a big issue with the VGG neural network, for example. However, it was resolved successfully in ResNet architecture, where authors just add so-called skip connections that preserved the information flow from vanishing. The second direction that is utilized in order to process some images and infer some predictions is recently emerged vision transformers. They are mostly based on a common technique that came from natural language processing. The key idea is the following, that we can split input image in some segments, organize them in the sequence, just like some sentence, for example, and fed directly into transformer encoder in order to predict something. In our case, to check whether in our image, in our patch of the image, uh, there is a car in some parking space or not. Okay, let's talk about the main specific designs that uh, were applied in the area of parking lot occupancy prediction. First of all, there were several attempts to implement really trivial architectures like AlexNet. They were successful, and the authors achieved quite good results despite the simplicity of the given approaches. Deeper architectures obviously performed better, but not significantly. Some specific approaches like contrastive feature learning and Siamese neural networks lacks of comparison with the other models, and the last one method was based on combination of heuristics and object detection model that extracts some bounding boxes of the car and compare them with the predefined locations of um, parking spaces. They were not so good as other models, but still, we will give them a try in our own study to show us better results. Common problem of the given approaches is the following. The data that was utilized before was quite limited in sense of specific data categories, and by the specific data categories, I mean the lack of proper annotations. We will reveal it in the next slides. So let's proceed to the datasets, what they contain. Exactly. The first one is the PK load, parking load dataset, the most common benchmark. But despite its distribution among the studies related to parking lot occupancy detection, it is not so expressive as others that we will discuss further because of its explicit simplicity. There are no so many occlusions, distortions, or any other kind of real world visual noise that make it very simple for CNNs or vision transformers to handle. Scenery Park is a better option to evaluate your prediction model because there are many different angles, a lot of occlusions between cars and trees, which is a common scenario for real-world application too. The last two published datasets are interesting. SMPS 2 times larger than PK lot contains some more hard to process data, but not as challenging as CNR Park. And the ACPDS dataset is the smallest. It's simply tiny. But however, it consists of images with perspective distortions, and there are a lot of categories of data, yet they are not annotated enough, good enough to use. As I mentioned before, common issues are problems with categories, with annotations, and the simplicity of certain benchmark that, despite of that, was used as the main approach, as a main benchmark in some studies. Okay, what categories were not established in our previous in the previous studies in the dataset related to them? First of all, it is winter data. Uh, it is challenging because of obviously some snow can cover cars, and these make predictions less reliable. Night is an option too in CNR Park and ACPDS. There are some images without any annotations and occlusions. Most of the biggest data sets tend to exclude such data, but in real world, again, we can frequently face such situation where we need to understand is some parking lot empty or not, just in the as in the right image in this slide. So how can we just overcome this problem? We need to add some additional annotations to our data. We need to extend the presented data by some additional tool. In order to do it, we established several IPython widgets that can be integrated in Jupyter Notebook. The first one allows us to add some annotations regarding the locations of parking lot, and the second allows us to add the labels to each of the previously defined areas where the cars can park. Finally, we established our own dataset SPKL, which contained half of the image regarding the winter data, and extend annotations of other datasets as follows. Finally, let's proceed to the architecture that we presented as our own contribution towards the parking lot occupancy detection problem. It is based on efficient net, neural network architecture that based on algorithm known as neural architecture search. It is just another neural network that is used to find the proper configuration of our CNN. Efficient net PID consists of 8 blocks. First 7 of them are the common blocks of EfficientNet B1, and the last one is our own addition. It is fine-tuned block regarding the our task of occupancy prediction. Well, um, let's proceed finally to the results that we obtained. Um, the first thing that I want to discuss is the intersection-based methods. As I mentioned before, they're not so reliable as classic binary classification tasks, mostly because of heuristic parts that utilized in them. And here we can see proper values of metrics for some of the configuration. However, there is a strong influence of stochasticity among different evaluation approaches, different backbone architectures, and different object detection methods in general. Uh, so let's shift to the main contribution of our work. It is results. It is results regarding the patch-based methods. And here I will give a word to my colleague Anastasia Martinova. Anastasia, please.
Thank you. Despite using specific method for training our vision transformers on small data sets, these models still performs unstable, as you can see. For example, a set of VIT models provide the highest result on all dataset except merged, but different modification achieve best result on different datasets. Especially interesting that non-pre-trained VIT outperforms pre-trained one on CNR Park and SMPC, which both are heterogeneous datasets, but doesn't surpass it on small SPKL. Thus, it can be supposed that this small dataset has the most complicated features. It means that this dataset may be used as the most realistic benchmark for testing real-world solution. As you can see, good results were shown by the VGG19 and MobileNet models, but the highest ones overall were achieved by our version of EfficientNet. It can be assumed that the scaling system allows it, obviously. We can say okay, thank you. In order to test the additional features of EfficientNet and increase values of metrics, we decided to try out several heuristics to train this model. The first one is batch-independent normalization. It is a just simple replacement of batch normalization step with the batch-independent step. It involves adding the standard activation step, one variable called proxy norm, which enables to preserve expressivity while compensating for the all channel-wise normalization channels. The second one is grouped convolution. It is just the use of multiple kernels per layer of image to help the neural network learn a diverse set of low and high level features. In our cases, we used parameter groups equal 16 in conf to the operation. The first heuristics is quite simple and involves changing the resolution of input images. We supposed that models trained at half image size can outperform models trained at native image size. Also, we tested different optimizers and stopped on RMS probe because it gives the best result. The next one is exponential moving average. It avoids sudden changes in model weights while training. So having previously created a copy of the weights after updating, we get the weighted average between the weights before and after the optimization step. And the last one is batch accumulation. It is simple accumulation of gradients and spreading them back every few batches. Next slide, please. We evaluated the effectiveness of our heuristics not just on the general validation sample, but for each category separately. As you can see from the histogram at the top of the slide, the largest number of images were in the occlusion tree and sunny categories. Let's examine their resultant head map. In some cases, the use of heuristics gave a slight increase in metric values. In general, the models worked best in the glare, overcast, and occlusion 3 categories, which was not obvious at first. The combination of heuristics that performed best on the total validation set, as you can see it denoted as best, as well as the combination of contrasting heuristics that denote as contrasting, never surpassed the results of individual methods, which seems to be an interesting result. And finally, the best results were shown by the exponential moving average heuristics, but guided by our given head map, you can choose the best method, especially for your data.
So, several words in conclusion of our study. Our first contribution is a new SPKL dataset that can be used as a new benchmark for parking lot occupancy detection problem. The second one is embeddable widgets for parking lot occupancy annotation. We hope that community will use it, and it will accelerate the annotation process and boost other studies in this domain. Additionally, we extended available datasets for parking lot occupancy detection with additional annotations regarding the 20 new categories. And the last one is our own method for predicting of parking lot occupancy that achieved the state-of-the-art performance and thus outperformed other solutions. Well, thank you for your attention. I am ready to answer a question.
Awesome. Well, thank you so much for first coming in to live to our studio today and for you joining us online for the first talk. I think my very first question is kind of like the future use cases of this dashboard right now. And I think about it, I'm picturing like not only the do I know of a parking lot has spaces before I arrive, but where in the parking lot is there typically going to be available places. So I'd love to hear what you think are the use cases
Well, it depends. Should we focus only on the parking guidance system, or we need to extend it even further? In the first case, okay, implementations of such parking guidance system is a big challenge. There are interesting results in China, for example, whereby the company implemented it in their well-known map system. Also, they have great results regarding, also mentioned in this talk, problem of future predictions of availability of parking lots. Such system can be used as the data extraction tool for this forecasting task. For the other domains, I suppose it is not so obviously useful, but time will show.
Awesome. And thank you so much for asking that question. And for the audience, that question was, how do you think this research is going to be the most impactful for AI in parking lots? I have one final question for you both. And what do you think the biggest roadblocks will be for applying this research? For example, like right now, there's millions of parking lots all over the world that all could use this data. So what do you picture as being the roadblocks there?
I think the main issue that we need to overcome in order to implement our results in the real world is local bureaucracy. In order to receive access to the proper number of video cameras and observation infrastructure, you need to go to municipalities and do some paperwork with them, which is not an option in some cases. In our own experience from Russia, it was hard enough to implement it in some regions, but however, in capital, it was way more easier.
Well, I think that was awesome. Thanks so much for coming into the studio today. Thanks so much for joining us online. I think that is all for that session. So, yeah, thank you so much for coming in. And now, quickly, before we go to a short break, we have two announcements here. First of all, you're at the Global AI Student Conference. For those who are listening in or have been here for a while, we have our Cloud Skills Challenge happening right now. The link is on the screen, but it's also aka.ms/learn-challenge. Through this, you can participate in the challenge, register, and you'll be on a leaderboard with everyone else listening in today from all over the world to go through some specific Microsoft Learn modules that were selected so that you can learn more about AI. We also have the opportunity for you to earn your very own learning badger at aka.ms/gai-badger. And by getting this badger, you can download it, add it to your own specific NFT wallet, and then you'll join a community of where there are over 13,000 badgers that have been redeemed worldwide. And with that, we'll go to a short break before coming back with our next talk.